we will see passive low pass filter. So we know what is passive. We know what is passive and we know what is low pass filter. Just before we get seen, now we will see the filter design. So the filter design is very simple. So you are putting one resistor and one capacitor, that is R and C elements, and you are designing this RC low pass filter. So if we connect the R and C in this patient, then this is forming a low pass filter. So you are applying the input signal here between these two terminals, and you are getting the output between these two terminals. So you are getting only low frequency signals here, and it stops all the high frequency signals from this input. So the frequency response is the same. It passes the low frequency, so the output is high when the frequency is low, and it stops when the frequency is getting higher and higher. When you increase the frequency here at the input, so it stops. And the cutoff frequency formula is FC is equal to 1 divided by 2 pi RC. So this is just the value of the resistor and capacitor. So how it works? At low frequency, the reactance of the capacitor, reactance, remember XC, that is the reactance of capacitor, is high, and it provides zero attenuation. So it means it provides zero attenuation, means it passes all the signals at the low frequency because the reactance value is high, and therefore input low frequency signal passes through and reach at the output. But when the frequency is getting increase more and more like this, then what is happening? The reactance value is decreasing. Reactance value of this capacitor is decreasing. So attenuation is also increasing. It means it starts to stop the high frequency signals. So the signal cannot pass through and pass through the capacitor and reach the output. So here, mostly you should remember this capacitor and its reactance plays an important role in this filtering operation. So in this way, it allows only low frequencies and attenuates high frequencies. So because at the low frequency, the reactance value is high, so it passes the low frequency signal at the output. But at high frequencies, the reactant value is the opposite, so it decreases. So it means the attenuation is increasing. So it starts to attenuate the signal. So the signal cannot pass through this capacitor and reach these output terminals. So remember, capacitor is a sensitive device. So it looks like a very simple device you may see in the lab, but this is a very sensitive and important device in the electronic industry. We are using this for many purposes in so many circuit designs, especially analog circuit designs. Whenever we design the circuits, mostly we try to avoid magnetic components and lossy components. So what are the magnetic and lossy components? Normally L, inductor, is a kind of magnetic and lossy components, and also the cost is high, the size is high, and also resistor. But resistor we cannot really avoid in the circuit design, so we must need, and we are using these resistors, but we try to avoid this L mostly. But we cannot also avoid L in all the circuits. For example, in power electronics, this L plays an important role. Okay, so this is not part of this course. We don't need to think about that. But just remember, capacitor is an important device. So in order to maintain the capacitance value, for example, this can be 1 nanofarad or 10 picofarad, whatever. So in order to maintain the capacitance value of the capacitor, it will always oppose a small amount of current flow in the circuit. This opposition to the current flow in the circuit is called impedance. So that also we know each component RLC, they have their own impedance. So that is nothing but their property of opposing current flow in the circuit. We can say that the capacitive reactance is inversely proportional to the frequency applied to the circuit. So if you remember this formula, Xc is equal to 1 divided by 2 pi Fc. So then you will understand what do I mean by here. So here you can see the reactance of the capacitor is high. So what is happening whenever you increase the frequency, this reactance value will decrease because this is inversely proportional, opposite. If it's directly proportional, then whenever you increase this one, this will also increase. So this operation, the low pass filtering operation, is really happening based on the reactance value of the capacitor. The reactance is reacting to the signal frequencies. So it passes the low frequencies and it stops the high frequency. So here in this patient, if you connect in the different way, then the operation will be totally different. Okay, so this means at low frequencies, the voltage drop is small and the voltage potential is large. So you are applying here. Now we will take the same example, what we had seen just before, 0 to 25 kilohertz. So let us say this is the low frequency. So at the low frequency, remember here, the voltage potential is very large across the capacitor, but the drop is very less. So when the voltage potential is very large, then we get the output signal here. But when you increase the frequency, instead of, for example, from 26 to 100 kilohertz, then what's happening? The potential across this capacitor is getting lesser and lesser, more and more smaller. So once the potential gets less, then definitely the output will go down. So that is what's happening here. So this is the property of the capacitor. So this is the standard property of the capacitor that you have to just remember. So so that is what mentioned here. So we are talking about the voltage drop with respect to reactance value. So that is what mentioned in this previous slide. But now we are talking in terms of voltage potential. So voltage potential is large at low frequencies, but at high frequencies, the voltage drop is okay. So voltage potential, we are talking about voltage potential only now. We are not talking about the voltage drop. So voltage potential is very less at high frequencies. Maybe you just forget this voltage drop. You don't need to think about two variables at a time. You just think about only one variable. So here we will just only talk about the voltage potential. So voltage potential is less at high frequencies. So it means for these frequencies, the voltage potential is very less. So we get the output as 0. So it means you do not get anything at the output because of less potential across the capacitor. In this way, this circuit allows low frequencies and blocks or attenuates high frequencies. So this low pass filter design is very simple. So you can easily remember. This is the phase and frequency response of RC low pass filter. Just to see here this graph. So when VO is equal to 0.707, what is 0.707? That is 1 divided by square root of 2. This is also the standard value. Try to remember. Times AF, we get the cutoff frequency. So cutoff frequency formula is 1 divided by 2 pi RC. So RC is, the R is the value of resistor, C is the value of the capacitor. So up to this value, up to the cutoff frequency, it will pass the frequencies at the output, the signal at the output. After the cutoff frequency, immediately it will start to fall down. The output will go to 0. Okay. So after the FC, if you increase the frequency, then what's happening? The output will decrease at the rate of minus 20 dB per decade. You can see here the output. This is the cutoff frequency of this low pass filter. And after the cutoff frequency, this output is falling minus 20 dB per decade. as I already told you, the voltage gain is measured by dB in terms of dB decibel. So this is the formula for the gain calculation. This is also the standard one in all filter designs we are using. So when the gain, okay, so here it's falling down minus 20 dB per decade. So you know what is decade means. So this is with respect to number 10. So in practical life, we are also using this decade. For example, the last decade I was in another country, something like that. So the decade means every 10 years. Normally we are using as a verb in the practical conversation. But here, so 20 dB per decade means for every decade, it will reduce 20 dB the output and it will just fall down. Okay, and after this FC, output is falling down. At the same time, phase will also change. So remember, we are applying in this phase means, and then at the output, the phase will also be different, something else. So here you can see here, this is the formula for phase shift in RC low pass filter. Phase shift is equal to minus tan inverse 2 pi f RC. So this is the formula for phase shift. So here 2 pi f is what? This is the omega. So tan inverse omega RC, I just put here 2 pi f RC. So here you just apply, if omega is equal to 0, then what will happen? So 0 multiplied by R and C values. So that is going to be tan inverse 0. So the totally everything is 0. So the phase angle is 0 degree. So it means output is in phase with input. So whenever this omega value is 0, there is no phase shift at the output. So whatever the input you are applying, the same you will get at the output. Okay, now if this omega value is equal to FC, cutoff frequency, then the phase angle is equal to minus 45 degree. So here you apply this omega value as FC value, that is the cutoff frequency. And of course you do some mathematical calculation here. So then you will get 45 degree phase shift. So here you can see the cutoff frequency. So at the cutoff frequency, in the middle point, you are getting minus 45 degree phase shift. So if you ask me this, what is the meaning of this minus sign? This is just indicating there is going to be a phase shift. And also in case if you are applying the input to the negative input terminal, also we are indicating this minus sign at the output. Now, if you apply the omega value as infinity, then the phase angle is equal to minus 90 degree. So that is what happening. Infinity means what? That is very high value. So you are applying more high frequency signals, then you will get the phase angle almost 90 degree phase shift. So here is 0 degree. So here we have 0 degree and we have 45 degree and we have the 90 degree phase shift. So then the output is almost 0 now. It's 0 at 90 degree, minus 90 degree. So now please try to remember and write it down. This cutoff frequency for low pass filter, this is the formula, and this is the phase angle formula. So here you can see a pass band and stop band. I told you whichever filter it is, it's passing certain frequencies, that is called a pass band, and it's stopping certain frequencies. That region is called stop band. And we can calculate the FC cutoff frequency value using the formula 1 divided by 2 pi RC. So if I calculate the cutoff frequency for this filter, maybe some specific value, maybe this is 50 kilohertz. So it's or 25 kilohertz. So it passes the signal and then it start to fall down at cutoff frequency value. So when the output meet this cutoff frequency value, the amplitude. So here you can see the voltage gain is minus 3 dB. That is the 0.707 times of AF. Simply we can also call here, if we talk about the V out, then we can call this is 0.707 times of input. If you assume the gain is a unity gain. So this is called minus 3 dB level. So at minus 3 dB level, we are getting this 45-degree phase shift, and then it's falling down sharply, and then it's just reaching the 0. This is for the first order filter. So here you can see the curve, the linear region is kind of longer. So now I want sharper region. Then what should I do? Before that, please try to also note down this formula. Output voltage V out is equal to V in times XC divided by square root of R square plus XC square. XC is what? That is the reactance value of the capacitor. So we had seen in this slide, we were talking about the reactance value, because everything is now the operation is depending upon the reactance value of the capacitor. So this is the output voltage formula for this RC low pass filter, and this is the cutoff frequency formula. So in this frequency response, we have the pass band and then the stop band. The bandwidth, it means that is the useful frequency that we are getting at the output. And we have the y-axis is indicating the gain in terms of dB, and this is the formula for gain calculation. And at cutoff frequency is meeting the dB at minus 3.